This video is sponsored by Siemens. Thanks, Siemens. When people think of cities, they picture glittering skylines, busy streets, beautiful parks, and underfunded mass transit. While these are all city things, none of it would be possible without the infrastructure under it all, particularly the wastewater system. Sewers, basically. For every bustling downtown, there's one or more of these wastewater treatment plants. Without them, cities would be smaller, smellier, and sicker. This video is an appreciation of the wastewater system. I mean, how often do we even think about wastewater? We just assume that the water going down there, or there, or there will just be taken care of. In this video, we'll get into topics like stormwater, bioswales, water treatment, and fatbergs. It won't all be gross, though. We'll also talk about the massive infrastructure projects going on underneath our cities and the infrastructure making our sewers more sustainable. Let's start with the basics. Cities have lots of water that people don't want to be there. There are two major sources of that water. The first is stormwater, typically rainwater falling on streets, roofs, parking lots, as well as the pervious surfaces like lawns and forests. The second is wastewater. This is the water that goes down the drain in kitchens and bathrooms all over a city. Let's start by talking about how stormwater is dealt with. How does all this wastewater get swept away from a city? There are several types of sewage systems, but let's look at the most common for urban areas. First, we have combined sewers. This is a common system in cities. It's basically a big old pipe running a couple meters below city streets. All of the wastewater, both wastewater from buildings and stormwater from runoff, gets collected into the same pipe. The manhole covers you see on city streets lead to these pipes. They're big, expensive systems that only make economic sense in urban areas. Combined sewers have been around for a long time. Rome's Cloaca Maxima is a great example. Originally built as an open sewer sometime around the 6th century BC, it was gradually expanded and covered over time. Eventually, wastewater from aqueduct use flowed into the facility, making it a true combined sewer. The Cloaca Maxima is technically still in continuous use, as a small amount of water is still transferred through it to the outfall near the Ponte Roto Bridge over the Tiber River. The name combined system provides a clue about the next system, a separate system. This is where wastewater from buildings gets its own pipes, called sanitary sewers, and runoff gets another set of pipes, called stormwater sewers. The sanitary sewer pipes travel to a wastewater treatment plant, while the stormwater flows back into the river. There are other systems out there, but combined and separate systems are the most common in cities. You won't find many open sewers these days, for example, because they're major sources of disease. These systems each have their own pros and cons, and some of the big ones are related to what happens after the wastewater is collected. In a combined system, all of the stormwater and wastewater reaches a treatment facility. Here, the wastewater is typically removed as solids. Then the facility removes suspended organic material, nitrogen, and phosphorus. Sometimes the remaining liquid is disinfected to kill bacteria. Then that liquid, far cleaner now than when it entered, is discharged into waterways. This works great normally, but during heavy rain events, there can be too much wastewater for the treatment facility to handle. What happens to the excess? Typically, all of that raw sewage gets dumped into a nearby river. These are called combined sewer overflow events, and they are not great for the environment, obviously. Separate systems don't really have this problem. All of the sanitary sewer material goes to the treatment facility, while the stormwater is collected and dumped directly into a body of water, bypassing any treatment. You don't get the black water, or the industry term for toilet waste, into the river, but stormwater isn't exactly clean either. It picks up oil and grease from cars, cigarette butts, litter, and whatever else is on the street. It's why you'll sometimes see flows to river painted near storm drains. It's to encourage you not to pour anything down that you wouldn't want to be swimming in later. The system with the longest history is the combined sewer, and big cities like New York, Paris, and London still use them today. Most systems installed after about 1950 use a separate approach. Neither of these systems have sterling environmental records. What can be done to make them better for our rivers and lakes? One of the most important things we can all do is not put things down drains that don't belong there. That means don't wash grease down the sink drain. Instead, drain grease into a can or jar and then throw it away after it hardens. In the bathroom, don't flush wet wipes, tampons, condoms, or diapers. They don't break down and create clogs. Some of the most infamous clogs in sewer history is a combination of all this stuff. I'm talking about the fatbergs of London. Fatbergs are giant masses of fat that form into a blockage when combined with diapers, wipes, and other debris. There's also an interesting chemical reaction taking place too. Wastewater often contains a lot of calcium, which it picks up when it runs over concrete streets and sidewalks and through concrete pipes. When that calcium water mixes with grease and fat, it transforms the fat into a dense mass thanks to saponification. This is the same chemical process that creates soap. The largest fatberg found in the London system was 140 tons and took workers weeks to remove. London launched a campaign to encourage people to put fat and wipes into the garbage cans instead. London's not the only city battling fatbergs. Tokyo had a fatberg wash out to sea in 2000 and since then have been educating their citizens as well. London's not just relying on education, they're also building a new super sewer to increase capacity and supplement the Victorian-era sewers that they rely on now. Those old sewers were a feat of engineering at the time, with 1,100 miles constructed out of 300 million bricks. The designers had the foresight to build the sewer for 4 million people, back when London only had 2 million inhabitants. Today, London's population is approaching 9 million, so you can see where the problem is. The pipes aren't large enough to flush out those fatbergs. Like a lot of cities, London also experiences many combined sewer overflow events that pollute their river. The new sewers will divert this overflow deep underground and send it to another treatment facility. London isn't the only city investing in massive combined sewer upgrades. Washington, D.C. is spending $2.6 billion to build an additional 18 miles of tunnel to reduce their combined sewer overflows by 96% in the region. It's the largest infrastructure project in the area since the Washington metro system opened in the 1970s. 2 tunnels have already opened, and the remaining tunnels will be open early in the next decade. Portland, Oregon completed its big pipe project in 2011 and reduced its outflows into the Willamette River by 94%. Seriously, if you Google CSO projects, you'll find links to all kinds of city websites that describe their sewer projects to stop dumping raw sewage into their rivers. Building big, expensive pipes, often called great infrastructure, is one way to solve environmental problems around sewers, especially the combined sewers that can trigger outflows. But in separate sewers, water from the street and parking lot goes directly into nearby waterways without any treatment at all. Recently, green infrastructure has been deployed in cities to improve the quality of stormwater before it enters the sewer system. One piece of green infrastructure that you've probably noticed in cities already is the bioswale. These facilities are essentially rain gardens placed in long, narrow spaces between the sidewalk and the curb. They take water from the street, store it, and treat it before the excess water flows into the sewer drain at the far end. Much of the water that would have ended up in the sewer just gets absorbed into the ground. Bioswales are planted with vegetation that could absorb excess nutrients like phosphates and nitrates. These compounds often cause eutrophication, or algae blooms, when they are dumped from the sewers directly into a waterway, so it's much better to filter them out in a bioswale. You'll also see cities with combined sewers building bioswales, retention ponds, green roofs, rain gardens, and permeable pavement to reduce the spike in wastewater that occurs when storms bring rain. These green facilities hold water and slowly release them into the sewer system, reducing the spike right after the storm and evening out flows. When thinking about wastewater and sustainability, it makes sense to think about water, but also electricity. About 3 to 4% of US energy consumption is used to move water around. Electricity is needed to power pumps and water treatment facilities. Reducing electricity use for wastewater facilities can also reduce carbon emissions and make the whole moving water around thing much more sustainable. Municipalities will often conduct an energy audit of a water system and find places where energy can be saved. Sometimes efficiencies can be found by repairing pipe leaks or improving systems to make existing machinery run more efficiently. Often, municipalities looking to improve efficiency and sustainability will opt to replace aging equipment with newer, more energy-efficient models. For example, Siemens, the sponsor of this video, recently worked with a municipality to replace a pumping station run by a steam boiler-driven system installed in 1901. Not only were these things near the end of their useful life, they were inefficient and not sustainable. Siemens switched the pumping station from boilers to modern electric pumps that will save the city over $4 million a year in operating costs. More importantly, the modern equipment is better for the environment. So there you have it. Sewer systems, the engineering marvels that made modern cities possible over 100 years ago, are becoming more efficient and sustainable in the 21st century. Old sewer pipes and boiler-driven pumps are being replaced by new sewer mega projects, bioswales, and better electrical infrastructure. It's good to know that cities are making these improvements to keep the clean water flowing from our taps and keep our toilets flushing.
Wastewater. It's what gets flushed down the toilet rinsed down the drain, and produced by places such as factories, workplaces, and homes. According to the U.S. Environmental Protection Agency, the average person uses about 100 gallons of water a day, with almost all of it turning into some form of wastewater.
Of the 100 gallons per capita per day of wastewater we produce, we are drinking about a gallon per day per capita. Essentially, wastewater is the 1 gallon of human waste produced per capita per day, diluted with 99 gallons of non-human waste.
Because wastewater contains pollutants and contaminants, most communities send it to treatment plants to be processed. The water has to meet federal, state, and local standards before it's released back into the environment. Wastewater is one part of the human water cycle, which describes the many ways people interact with nature's hydrologic cycle to meet our needs for water, food, and energy. While water treatment plants are a necessary part of public health and environmental safety, they require a great deal of energy and resources to operate.
In the US, we devote about 3 to 6% of the national energy budget on the enterprise of clean water.
Kartik Chandran is a professor of Earth and Environmental Engineering at Columbia University and funded by the National Science Foundation. He investigates new, more efficient ways to treat wastewater. Wastewater contains elements such as phosphorus, organic carbon, and nitrogen, which are often removed during the treatment process.
Well, let's start with nitrogen. When we want to remove nitrogen from wastewater, in addition to the organic carbon, the energy footprint of a wastewater treatment plant essentially doubles.
At the Newtown Wastewater Treatment Plant in Brooklyn, New York, treating wastewater involves several steps. First, the system separates floating matter and solids from the water. The remaining sewage then enters an aeration tank.
What we do in aeration tanks is we supply oxygen to microorganisms that actually treat the sewage.
Typical microbes for wastewater treatment require oxygen to degrade organic pollutants. The resulting sludge is further treated, and in its final step, the water is disinfected. Chandran is trying to reduce the amount of energy used in this process. He uses a type of bacteria found in wastewater called anemox. These organisms don't need oxygen to remove nitrogen from wastewater. While traditional wastewater treatment often releases greenhouse gases such as nitrous oxide and carbon dioxide, using anemox bacteria does not.
They allow us to remove nitrogen at far lower energy costs and chemical costs. Not just that, we would save 60% in terms of aeration costs if we use the anemox model for removing nitrogen.
Chandran and his team are also looking at ways to use wastewater's abundant chemicals, nutrients, and other resources to produce energy.
We have been able to convert the organic carbon in food waste, in sewage sludge, in fecal sludge to biodiesel, which is a liquid fuel easily transported and easily used, directly used in diesel engines.
The Newtown Wastewater Treatment Plant is already producing energy from organic material.
The digesters are heated to about 95 degrees Fahrenheit. They act like the human body. They break down the organic material, and we provide no oxygen. And one of the byproducts of the digestion process is methane gas.
Methane gas is a common energy source.
We are right now using a good portion of our digester gas to heat our boilers at our locations. The boilers are used for heating the environmental areas, the personnel areas, and they're also used to reheat the digesters.
Chandran and his team are also finding additional uses for wastewater products. For example, they are using the organic carbon found in wastewater to develop bioplastics and taking the phosphorus and nitrogen from wastewater for use in irrigation.
By linking the water sector, the energy sector, the food sector, and a few other sectors, we are now able to address these challenges not just one by one, individually in isolation, but together in conjunction. That's a very sustainable model.
As Chandran and his team help make the human water cycle more energy efficient, they are also helping us see wastewater not as waste, but as a precious resource.
It's a topic we'd rather not think about. Where does last night's dinner go when we flush it down the drain? While you may already be grossed out just thinking about it, this question leads way to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, you may be thinking that you'd rather just let bygones be bygones and not think about this nasty part of real life. But here's the thing. Chances are you've drunk water that was waste at some point, so you might want to take some time to understand this engineering process that makes dirty water clean. Here's where it starts. The toilet. Once you're done doing your business and flush that magical handle, your waste ends up at the inlet of one pretty interesting place, a wastewater treatment plant. Why is this place so interesting? Because it takes arguably one of the most disgusting substances in the world and turns it back into something that is essential to all life. Flushing just your toilet at halftime may not seem like a big deal, but when you couple it with thousands, if not millions, of others doing the same, it can result in some pretty high sewage flow rates. New York City has an array of 14 wastewater treatment plants that handle a combined 1.3 billion gallons of wastewater daily. That's enough wastewater to fill the Dead Sea with pure sewage in just 8 years. And that's just New York City. There are an estimated 14,748 treatment plants in the US alone that 76% of the USA's population relies on, according to the American Society of Civil Engineers. Understanding wastewater is crucial to understanding the critical infrastructure needed to support modern life. That brings us to the first step of the process that handles larger items in sewage, things like flushable wipes, 2x4s, toys, or even guns. You name it, and it's probably been caught in a bar screen. Bar screens are exactly what you would think. They are large vertical bars that stand at the inlet of nearly every wastewater treatment plant, designed to stop larger items from getting to the plant and hurting machinery like pumps. This first process where bar screens are used is commonly referred to as pre-treatment. The sole intention of pre-treatment is to remove the outliers in the sewage and make the whole mixture a little more homogeneous, or slightly less chunky. Bar screens are typically mechanically raked at certain intervals, depending upon the flow rates of the water treatment plant, although some older plants will still have more manual removal processes. Whatever is removed from the bar screens is then sent off to your average landfill or solid waste handling facility. Or, in the case of unusual items, such as guns, they're sent off to the evidence locker in a police station to be investigated. Next up is the grit chamber. Grit chambers are the next steps in the pre-treatment process following bar screens. Since these bars don't catch everything, larger particles called grit still need to be removed from the sewage as it is made even more homogeneous. As the sewage flows into the grit chamber, the velocity of the rather viscous sewage is adjusted to allow for particles of sand and rock to settle out. This is needed because these particles can't be removed using chemicals, and they could potentially clog or destroy pumps later on in the process. There are 3 types of these chambers: horizontal grit chambers, aerated grit chambers, and vortex grit chambers, which all accomplish the same task using slightly different methods. Following the grit chambers, the sewage will move on to the primary treatment process, which starts with a large basin called a primary clarifier. Primary clarifiers, and clarifiers in general, function on the principle of settling velocity. This term can be defined simply as the speed at which a particle settles. For wastewater being pumped into clarifiers, it's important that the flow rate of the water being pumped in doesn't exceed the settling velocity of the particles trying to be removed. In order to accomplish this, engineers will vary the size and number of primary clarifiers in accordance with the plant's permitted sewage flow rate. This ensures that at varying flow levels, solids can settle out of primary clarifiers to the correct quantities. At this step in the process, the slightly treated wastewater, which is referred to as effluent, is free of solids larger than 10 micrometers and should be all organic matter, which will be treated further. The top layer of the clarified water flows over a weir wall and into the next basin in the process, called the aeration basin. Now begins the process of secondary treatment, the sole focus of which is to significantly degrade the biological content of the sewage. In many cases, this process starts with aeration basins. Effluent flows into the aeration basins, at the bottom of which are hundreds, if not thousands, of tiny air blowers that create bubbles through the water. The water is pumped into this tank along with something called return-activated sludge. You can think of return-activated sludge as a bunch of happy little bacteria that get to eat their favorite foods all day long. This introduction of significant amounts of bacteria along with the massive amounts of oxygen injected from the bubblers creates an environment perfect for the process of aerobic digestion. Summarized simply, it's the breakdown of organic matter along with the use of excess oxygen. Some older plants will add in another step before aeration basins referred to as biofilters or trickling filters. Found in many older plants, these filters essentially trickle the effluent over a medium like stone or plastic and allow for a film of bacteria to chow down on any organic matter in the water. This step is largely not used in newer plants due to more efficient and effective modern processes. But for plants with basins already installed, many still use them because they only benefit the treatment process in most cases. Following aeration basins, the effluent along with much of the sludge is pumped into a secondary filter or clarifier, where some of the sludge is removed and pumped back into the aeration basins as the return-activated sludge. Further settling of larger particles is also accomplished in these basins, as it is the final step of the process that will remove solids and larger biological matter. Water flows out of secondary clarifiers over a nearly identical weir wall to the primary clarifiers and moves on to the disinfection process. At this point, 85% of all organic matter is removed from the water, and the effluent should be safe to drink in most cases, although you probably wouldn't want to. Disinfection is the final step of the process and is usually accomplished in one of three ways, either through chlorine, ozone, or ultraviolet disinfection. Each process has its benefits and drawbacks, with each being used commonly throughout the wastewater treatment process across the world. Chlorine disinfects the water through chemical disinfection. Chlorine, which you can think of as concentrated bleach, is added to the effluent here to kill off any remaining bacteria and organisms still living in the water. When chlorine is added to kill off the bacteria, it then has to be removed before it can be discharged, as to not kill off anything in the discharge location. After this, the water is safe enough to discharge into a stream or lake. Ozone disinfection is another method of disinfection that involves pumping an electrical current through the water that causes oxygen molecules, O2, to disassociate and combine with a free oxygen molecule, forming O3, known as ozone. Ozone is an incredibly strong oxidant and causes microbes' cell walls to leak, rapid cell decomposition, and overall damage to cells. In other words, it kills off bacteria. The last common method uses ultraviolet light to scramble bacteria's DNA so that they cannot multiply. In UV disinfection, the bacteria in the water aren't killed, rather they're sterilized, rendering them harmless. If you were to ingest water with living microbes immediately following UV treatment, any harmful bacteria would be unable to multiply or render your body damage. Engineers choose between these methods based on a variety of factors such as flow rates, cost, and location of discharge, which brings us to the final step, effluent release. Effluent release exists in one of two forms. In most cases, the now treated water is released back into a stream or lake or other water source. In rare cases, usually in areas where water is scarce, the effluent discharge from a wastewater treatment plant can be discharged into another treatment plant directly, where it will be treated further for consumption. This is referred to as full-cycle water reuse. From a chemical perspective, the final drinking water is the same as normal treated water that flows through your pipes now, but due to the connotation of your drinking water being sewage just days before, this treatment process is normally shied away from or not heavily publicized. The entire process of wastewater treatment takes on average 24 to 36 hours from when a drop of water enters to when it leaves. Each wastewater plant will receive a permit for flow rates, chemical levels, and effluent quality, among other things, from the EPA that outlines the necessary treatment for a plant. Wastewater plant operators will make adjustments to a plant's operation and constantly measure levels to ensure proper discharge and proper treatment. Without these operators and the dirty job that they do around the clock, our sewage would always stay sewage, and sanitation in modern cities would be much, much worse. Wastewater treatment is an essential dirty job, and you can thank the 14,748 treatment plants in the US alone for not having to worry about what happens when you flush.
Welcome to the Ventura Water Reclamation Facility. My name is Vince, and I will be your virtual tour guide on today's tour of our plant. Every time you flush the toilet, wash your hands, take a shower, or do your laundry, that water all comes to this facility to be cleaned before we discharge into the Santa Clara River estuary. We treat roughly 7 to 8 million gallons a day of wastewater. Today, our tour is going to consist of following the liquid stream and the solid stream throughout our facility. Our first stop brings us to our headworks facility. This is where all of the wastewater from out the city comes to our facility. Here, we remove large items such as rags or paper towels and grit, which can pose issues to the treatment system further on. Let's go inside and take a look. This is the bar screen. The bar screen system picks up paper towels, rags, and puts them onto a conveyor belt to be hauled to a landfill. The grit and rags that are collected from the bar screen enters the grit box, which will be hauled off to a landfill for final disposal. After the water leaves headworks, it comes to the primary clarifiers. This is where we get the main separation between solid and liquid. So behind me are the primary clarifiers. These use gravity to separate the liquid and the solids. Anything that's heavy sinks to the bottom, and any light material or water stays at the top to go move on to the next process. So from this point on, the water at the top is going to go one way, and all the solids that are at the bottom are going to go another way. So from here, we're going to have two different streams. We're going to have the water stream, and we're going to have the solid stream at the bottom. So now we're going to follow the water stream, which is going to take us to our activated sludge tanks. Come on, let's go. The next step in our treatment process is the activated sludge tanks. In these tanks, we have good bacteria and bad bacteria. The good bacteria eats the bad bacteria. So we have to maintain a constant balance of good bacteria versus bad bacteria. All organisms need three things to live: food, water, and air. Since this bacteria needs air to survive, we pump air through the bottom of the tanks so they can breathe. This process consists of two main objectives: nitrification and denitrification. In the nitrification process, we convert ammonia into nitrate. In the denitrification process, we convert nitrate to nitrogen gas. Nitrate is dangerous to the wildlife where the water will flow after it leaves the plant. So it's very important for us to take that nitrate out of the water and convert it into nitrogen gas. This is the main step of our biological treatment process. During this process, we don't use any chemicals. From this point, we're going to go to our next step, which is the secondary sedimentation tanks. This treatment process is called secondary sedimentation. This is just like primary sedimentation, but the bacteria that's in the water sink to the bottom very slowly. As you can see here, the water will overflow the weirs and then go on to the next treatment process. Anything that doesn't go over the weirs settles to the bottom and is reused and recycled into the aeration system. As you can see, we have our local wildlife that enjoys our secondary sedimentation tanks also. The water that goes through the weir comes over our waterfall and then flows underground to the next step in our process, the tertiary treatment filters. These mixed media filters are made up of different types of sand and gravel. They clean the water to where it can be reused for irrigation and landscaping purposes. The water moves through these low pressure filters and remove all inorganic compounds. So far throughout this process, we still haven't used any chemicals. From here, the water is going to flow to our chlorine contact tanks. This brings us to the last stage of our wastewater treatment. Here, the water is disinfected with chlorine. So basically it smells like a swimming pool. These chemicals have to be stored in a facility for safety purposes. Any other living organisms that make it to this point are killed in the disinfection process. So the water has to remain in these tanks for a certain amount of time in order to chlorinate the water properly. Once the water leaves this tank, we have to dechlorinate the water, which means take the chlorine out of the water so it's not harmful to the birds in the receiving water. To do that, we use sulfur dioxide to dechlorinate the water. Once the water is dechlorinated, it can be released to the wildlife ponds and then ultimately to the Santa Clara River estuary. When the water first entered our facility, it was dark and murky. Now it is clear, clean, and safe for the environment. So that's it for the liquid portion of the tour. Now we're going to talk about the solid portion. Remember the part that we talked about in the primary clarifiers that settles to the bottom? That ends up here in the digesters. These digesters work like stomachs. They have to maintain a certain temperature in order for the bugs to live and break down the bad contaminants that are left in the sludge. The bacteria in these tanks create methane gas. That methane gas is captured and we're able to generate electricity from it. That process is called cogeneration, where we power an engine using methane gas as fuel, which in turn turns a generator to create electricity. Using this treatment process, our plant is able to generate about 30% of our electrical needs. So that concludes our tour of the Ventura Water Reclamation Facility. I'd like to thank you for taking this virtual tour. Hopefully soon, you'll be able to take a tour in person here at the plant.